Hi, I'm Matthias Beck. I'm one of the authors of Computing the Continuous Discretely, and in this video we will talk about rational polytopes and their Ehrhart quasi-polynomials. Our setup, and in fact the proof of Ehrhart's theorem in the rational case, will follow the same steps as in the lattice polytope case, which we discussed in the previous video, but there are some subtleties that I want to point out now. So again, I'm starting with a polytope in R to the D, given as the convex hull of n points, but now I'm assuming that these have rational coordinates. The next step, as before, is to lift these vectors into D plus one dimensional space. So these now will be rational vectors with a 1 as the last coordinate, living in dimension d plus 1. Now I'll cone over this polytope. So you can think of the original vertices as being here at height 1. But now remember, those are rational vectors. So the first thing we'll do is we'll replace this description of my cone over P given by rational generators by making each of the generators integral. So instead of maybe having this generator, I might scale it. Let's say this rational point here had denominator 2. Maybe down here is a vertex that actually already had integer coordinates, and maybe another vector I have to scale by a factor of 3, let's say. Yeah, so I take each of my generators and scale them to have integer generators. I want to point out at this point is that the scaling will change the last coordinate. And in fact, there's a quantity that's going to come into play. This is called the denominator of P. So this is the least integer amount that I have to scale P such that all of my new vertices, or in the cone, the new generators, will become integer vectors. So it's the minimal positive integer k, such that I can phrase it like Kp is a lattice polytope. So if you think of my example on the right, you can see that I scaled my generators, I rescaled my generators to different heights. So the height is what I like to call the last variable, because I think of this as an additional dimension and then sort of moving up in that dimension. But now what I could do is I could rescale this picture further to have each of my generators in the cone at the same height. And a minimal such height is precisely the denominator of the polytope. We will go with this picture now and see what happens with the setup from last time. Okay, so let's say we have a polytope, a rational polytope P with denominator K. The first thing we did in the previous video is to form the cone over P and then triangulate it. Or if you will, you can triangulate P and then form the cone over each simplex. And then for each simplicial cone in this triangulation, we use this theorem. Okay, I think of cone over P as written in terms of generators that are all at height k. They are all integer generators whose last coordinate is k. And I will do the same thing with the simplicial cones in my triangulation. all of these vectors now, for each simplicial cone, are integer vectors with height k. So once more, this means the last variable is k. And now this theorem 3.5 says the integer point transform is a rational function, and I can express this rational function in terms of the fundamental parallelepiped, and then in the denominator I see my generators. And then from there we specialized this integer point transform at 1, 1, 1 and kept only the last variable as a variable. And what you will now see is that I will pick up, for each generator, I will pick up this last variable to the height. And this is where my assumption comes in, that I consider each generator at height k. So I have a uniform last variable over here, which gives me this denominator 1 minus z sub d plus 1 to the k, all to the power d plus 1. Now I proceed as last time, so I'm going to piece these rational functions together. Maybe I'll triangulate smartly, do a little shift so I don't have to subtract. At any rate, what appears here at the end of the day is, as we know, the Ehrhart series of p. And because all the rational functions I'm summing have this same denominator, my rational function version of the Ehrhart series also has denominator 1 minus z to the k, all to d plus 1. And I have some polynomial in the numerator, and this is also called the h star polynomial. So if you compare this to the lattice polytope case, the quote-unquote only difference is this power of k. And now if you work on this type of generating function representing this Ehrhart series, you can realize that the Ehrhart counting function, the original counting function in this generating function, is a quasi-polynomial. And this parameter k becomes the period of this quasi-polynomial unless I can cancel some things in this rational function. So Ehrhart's theorem in the rational case is, if you give me a rational polytope of denominator k, then the Ehrhart counting function is now a quasi-polynomial. The degree, as before, is the dimension of the polytope, and the period now divides the denominator of p. Let me finish this video by picking up a thread from an earlier video, namely that an Ehrhart polynomial or an Ehrhart quasi-polynomial is given by a finite set of data. It's a discrete counting object. And again, I want you to think about this, keeping in mind that on a very basic level, we're computing a volume here. And so let me repeat that one of the magic consequences of Ehrhart's theorem is that we can compute this continuous volume in a completely discrete fashion. So I'm thinking about the situation where P is a lattice polytope dimension D. And a sort of philosophical question is, what does it mean to know the Ehrhart polynomial of P? Well, by now we know the constant term of this Ehrhart polynomial has to be 1. So one answer to this question is to know the D remaining coefficient of this polynomial. But we also might be given the roots, or we might compute the roots of this polynomial. And again, because we know one coefficient, this determines the polynomial. In section 3.7 in the book, we discuss interpolation of an Ehrhart polynomial. As you know, you can compute a degree D polynomial by interpolating D plus 1 given values. Again, in this case, one of them is given to us for free. So if we know the integer point count in the polytope, in twice the polytope, and so on, up to the dth dilate, if we know these d values in addition to the constant term, we in principle know the polynomial. Another encoding of the same information is in the generating function. So this is what we call the Ehrhart series in this case, but if you think about polynomials, you should just think of this as the generating function of the polynomial we're computing here. We should note that we know this constant term of this numerator polynomial. At any rate, again, all the information of the Ehrhart polynomial is encoded in this rational generating function, and a pointer towards this fact is that we know this rational generating function, at least in this case, if we know the numerator polynomial, which is a polynomial of degree less than or equal to d. And in fact, we can make this more concrete because you've probably done this calculation that you can retrieve the Ehrhart polynomial from its Ehrhart series, rather from the h star polynomial, the numerator of the rational generating function of the Ehrhart polynomial, in the sense that we can write the Ehrhart polynomial as a weighted sum of binomial coefficients. And so really the step of going from the coefficients of the Ehrhart polynomial to the coefficients of the Ehrhart series is a linear transformation. It's a change of basis. You can think of this linear transformation as changing from the standard monomial basis to a different polynomial basis, namely the polynomial basis given by these d plus 1 binomial coefficients as functions in T. So what about the rational case? So now I think of P as a rational polytope, again, dimension d. So in this case, the Ehrhart counting function is a quasi-polynomial. Let me remind you that this means that we can write down this function in the form of a polynomial, but now my coefficients are not constants. These coefficients are periodic functions in T of some period. Let's say they have a common period k. Here's an alternative way of writing down a quasi-polynomial. Namely, I can think of a quasi-polynomial as a list of polynomials. So what you see here on the right, these functions p0, p1, and so on, are actual polynomials. And my quasi-polynomial goes through this list of polynomials in a cyclic fashion, depending on what t is modulo k. These polynomials are called the constituents of the quasi-polynomial. I like this name. And once more, we can think about what does it mean to know a quasi-polynomial. So in the first formulation, we have d plus 1 coefficient functions. Each has period k. So we need to know a total of d plus 1 times k pieces of data. And if you think of my constituent polynomials, again as polynomials of degree d, I have k of those constituent polynomials. So again, it's a total amount of d plus 1 times k pieces of data that I need to know to determine the quasi-polynomial. As before, I could now think of this data as given by roots of, let's say, the constituent polynomials, or I can do interpolation. Now, if I want to do interpolation of a quasi-polynomial, I need to know d plus 1 times k pieces of information. So that might be, for example, the evaluations at 0, because I know this is 1, then at 1, and at 2, and so on, up to the evaluation at k times d plus 1 minus 1. Finally, my Ehrhart quasi-polynomial might be given to me in the form of the Ehrhart series, the generating function of this quasi-polynomial. And we've seen that the Ehrhart series in the rational case evaluates to a rational function where I can see the period of the quasi-polynomial here in the denominator and the degree over here. And so the h star polynomial now, the numerator of the rational generating function, has degree at most k times d plus 1 minus 1. This is maybe the most compact way of writing down the information of an Ehrhart quasi-polynomial. At any rate, you can see again that however we're given a quasi-polynomial, we need k times d plus 1 pieces of information. And then again, like in the polynomial case, there's various ways of moving between one representation to the other.